All right, everybody, we're going to get started again. You all have been a delightful audience, and we have one more talk to round out this first session. We are thrilled to have Dr. Benjamin Bengfort here to talk about practical multi-arm bandits. Dr. Bengfort is the co-founder and CEO of Rotational Labs, where he orchestrates the integration of machine learning techniques with advanced distributed computing systems. He has expertise in systems engineering, programming, data science. He's a big believer in open source. Dr. Bengfort pays special attention to the ethics and outcomes of AI, ensuring humans are at the center of all our solutions. He is the co-author of Applied Text Analysis with Python, as well as Data Analytics with Hadoop. He earned his PhD from the University of Maryland with a focus on planetary scale distributed systems, which I would also attend a talk on. So with that, please join me in welcoming Dr. Bengfort.
Hello, everyone. So today I wanted to share with you all a tool that I use on a fairly regular basis. And I really love this tool because it's great for creativity. And so that's what I hope I'll communicate most today is the creativity of problem solving using multi-armed bandits as a solution. So I guess we should get started and maybe talk about what is a multi-armed bandit. In old-timey talk, a bandit is a slot machine, so-called a bandit because it takes your money from you. And those slot machines used to have arms on them that you would pull, right? And then the things would spin, and if you got 3 in a row, you would win, but you would never win, so it was a bandit stealing your money. So the problem definition for a multi-armed bandit is, let's say that you're in a room with n number of these bandits, these slot machines, and you know for a fact that one of them will pay out jackpots or will pay out more than the others. The question is, how do you figure out which bandit that one is? Or, I mean, maybe said even more mathematically, how do you maximize your expected value as you're pulling these arms? And the algorithm is actually deceptively simple. You assign each bandit uniform probabilities, right? When you know nothing, we assume that they are all equally likely to pay out. Randomly select an arm, pull it, and then update your probability distribution based on the outcome for when you pull the arm. It is extremely straightforward and very easy to implement. And this is one of the reasons it's such a great tool to use. Just what happens, though, is the devil is in the details with these kinds of things. And so that's most of what I'm going to be talking about is the devil. The first detail that you have to think about is this trade-off. And anytime you read anything about multi-armed bandits, you're going to start to hear about the exploration versus exploitation trade-off. Right? So what if there are some bandits that are paying out like, okay, you don't really know if that's the one or not, but you do have one that's paying out really well. So how do you switch to that one bandit that's paying out really well and exploit it, right? Get as much money out of that bandit as you can versus when do you keep exploring to try to figure out what is the best bandit that exists? The primary algorithm to do this is something called the epsilon greedy algorithm. So what you do is you introduce some parameter epsilon, and with some probability epsilon, you will select the best arm. Otherwise, you will explore, right? And you don't want to just fix that in time. You want to decrease epsilon over time so that you do less exploration and more exploitation as you go. There are variants of the epsilon greedy algorithm that include things like distribution sampling, where you can use upper confidence bounds using uncertainty to influence exploration. So as your UCB increases, you have more confidence that you found the right arm, and so you stop during exploration. Or you do Thompson sampling. You model each arm's reward distribution, and then that's the probability selection that you take. Now, I will say in practical implementations, everything that I've done has been a combination of epsilon greedy and Thompson sampling, right? It's not just the probability of outcome, but if you can model the rewards as probabilities, then you can use epsilon to choose based on the probability distribution from the reward sample. Otherwise, simply select the best arm, right? And so it tends to be a combination of Thompson and epsilon greedy. Now, with all parameters epsilon, you'll see that there is a big trade-off. So some nice properties about bandit algorithms are that they will converge to a solution. But like most of the data science algorithms that you've probably heard of, just because it converges doesn't mean you found the best thing, right? So you can get stuck in local maxima. The real thing when it comes to multi-arm bandits is really thinking about the speed of how fast you get to that sort of best location. And I'll talk a little bit more about that in a section. So this graph shows sort of the total rewards over time. And uniform random selection is this purple line right here. So hopefully what you can see is that all the other color lines, they are the bandit algorithms. They all end up having a better reward than uniform random selection, right? Just always randomly selecting something. But you can see that different epsilons influence the speed at which you get to that better distribution, right? So if you have, a very low epsilon here, right, you spend more time exploring and less time exploiting, and it takes you longer to sort of get over that uniform random selection hump. So, that's sort of multi-arm bandits in a nutshell. Where you will commonly see or hear about multi-armed bandits is click-through rates, right? And measuring engagement, right? So this is the primary thing. I'm sure everyone here has heard of A/B testing. Multi-armed bandits are usually considered as more complex A/B testing, right? So an example from the Netflix blog: if you had A/B testing, right, we have two thumbnails, and the question is, which thumbnail will get people to engage with this content more, right? Is this thumbnail for Good Will Hunting better than this thumbnail for Good Will Hunting? You can do A/B testing on that. With multi-armed bandits, though, you can do far more thumbnails, right? It's not just an A/B test. You can have 9 different thumbnails to see which performs better. So just in case there's folks in the audience who are doing this style testing, I do want to talk about the differences between A/B testing and multi-armed bandits. So with A/B testing, you have to have 2 fixed groups in advance of your experiment, right? So those groups have to be assigned at the beginning, and members of the groups can't switch groups. The first question that you ask in A/B testing is there a significant difference, right? That's the very first question. And you can't do anything until you get past that question. So A/B testing is good in a situation where you have a sort of long-term longitudinal study where there's no change, and you really want to exploit faster by answering that, do things change? Multi-armed bandits, on the other hand, are dynamic. You do not have to assign the groups in advance. In fact, you can assign as they come in based on those probabilities, right? It's also, you update in real time. So multi-armed bandits are more of a real-time experiment, and they are much faster at coming to these dynamic conclusions. And importantly, you don't have to fix the experiment time, right? Which leads to an important variant on, I guess the variant is contextual bandits. But I will say that, that act of dynamics really makes multi-armed bandits a form of machine learning. For those of you who are more mathematically or theoretically inclined, you can model multi-armed bandits as a Markov decision process. And because you can do that, it does fall within the category of reinforcement learning, where you have an agent interacting with its environment in order to achieve a goal. And if you think about the Markov decision process, what you need is you need some sort of environment, right? You need somewhere where your software application is running. So you saw with Netflix, the Netflix dashboard, that's the environment. You need a policy, right? You need to output actions based on observations. So that's what thumbnails am I displaying for these images. And then you need an agent. You need something in the back end that's looking at the outcomes and it's updating those policies based on the observations and the rewards. However, I will say that because this is a class of reinforcement learning, I hope that what we'll all see tonight is that this is actually an algorithm that's well suited to a lot of different types of problem solving and goes well beyond things like marketing and engagement, click-through, and that kind of stuff, and is often a simpler solution to real-time learning than doing like static learning or supervised learning or clustering or something like that, because you don't need to know the parameters in advance. You go for it and hope that something good comes out of it, and often it does. The last thing I wanted to mention, and again, this is just to make you dangerous for Googling, is this idea of contextual bandits. So if we go back to the Netflix example, if we A/B test a thumbnail, right, that's just for the entire, like which of these thumbnails is better for like everyone. But you can kind of see that, well, things aren't necessarily better for everyone, right? Some of these thumbnails might be better for some groups. Some of these thumbnails might be better for some groups. So contextual bandits augments the arms with a contextual vector. So you actually have more information about the environment at the time of selection or arm pulling on the bandit. And that informs how the policy chooses the action. And so this leads to personalization, right? So it's a contextual bandit is a bandit on top of bandits. So you might think about having multiple policies, and each of those multiple policies has arms. So the first thing you have is a bandit that selects the policy, and then the policy selects the arm. Now, the very interesting mathematical term that we use to measure contextual bandits is this idea of contextual regret. And the reason it's called regret is because regret is the measurement of the reward that you get from choosing a contextual policy instead of choosing the best arm. And there's an idea that, the best arm would have a higher reward, except that you have this context, so you choose this other arm. And so that difference is the regret, right? The difference in rewards. In practice, it's the exact opposite of regret, right? In practice, user customization, like it's actually a better reward. This policy is better for me, right? I actually get less reward from the generic mean aggregate case. I get more reward. So even though it says regret, it can actually be a good thing. Depending on the type of environment you're working with. So if you're looking, again, so I mentioned Googling, these are sort of the algorithms that are used for contextual bandits. So X4, it's 4 E's, and I can never remember them. Exploration and exploitation are 2 of the E's, and I can never remember the other 2 E's, but it's basically what I said, bandit on top of bandit is what X4 is. And it's an extension of an older algorithm called X3. Lin UCB is linearized upper conditional bounds. So that's a contextual extension of the algorithm I mentioned in an earlier slide. And then this is the brand new one. I love to con bandits because we do have to come up with good names for our algorithms. But I love to con bandits is the new algorithm that performs well for really large number of arms. And so that's the one that I would recommend if you are doing contextual bandits is to look into I love to con bandits. The last thing I want to talk about before we get into some of the details of this is dealing with change, right? So one thing that happens is, as you start, you're doing more exploration than exploitation, and then you get to this point where you're doing more exploitation than exploration. The question that probably immediately leaps up to us is, well, what happens if things change, right? What happens if the user preferences change or if the dynamics change? And this is actually a really hard problem. So there are 2 primary techniques that I use, right? Anomaly detection and periodic native learners. There's also a style of problem solving where you limit the duration of a bandit so that, you don't have to worry about change. Like the bandit only runs for so long and then we restart the bandit. That's kind of another way to do it. Or one of the examples we're going to look at is prioritizing sprint tasks during the sprint. So that bandit would only run for, 2 weeks before it's reset. So you don't have to worry about change in that context. But if you have some long-running algorithm, you have to figure things out. So in order to reprioritize exploration, you really only have two choices. The first is anomaly detection. So anomaly detection is a hard reset of your distributions and epsilon. And so you would use something like, a one-class SVM or an isoforest or something to do anomaly detection, and then use that as a trigger to reset and restart the bandit. And that is kind of the nuclear option because you're going back to scratch and rebuilding from scratch. But that tends to work okay, especially if you have a lot of arm pulling that happens very rapidly. The other thing you can do is you can use something called periodic naive learners. So you basically subset your population and you subject them to a new learner, right? So in parallel with the old learner, you subject a subset to the new learner, and then you compare the outcomes of the new learner to the existing learner that's there. And so the questions are, do we have a new or fundamentally different probability distribution, or do we have like a new policy interaction that has changed? And so those periodic naive learners can help you kind of bootstrap the process, but that comes with problems of its own, right? So because we are conducting actions and then looking at the rewards from those actions, we can't simulate anything because the actions depend on the rewards depend on what actions were selected. So there's no way to simulate historically because the user will just choose the same thing historically and it'll go the same way. And then you have this other question is like, is it apples to apples? Like, is my subset, does that match the dynamics of the larger population? So you kind of have to jump through those hoops, but it does at least allow you to bootstrap things without going the full nuclear option. Okay. So let's get into the meat of implementing Bandit applications. And the biggest thing that I want you guys to take away from this is that, one, Bandit applications are simple, but they allow you to be very creative and to get things into production get experiments into production very quickly. Now, I contemplated adding some Python code here in order to show you what this might look like. And so I went through some of our experiments that we had and started looking at the Python code. And I realized we don't use any libraries for this, right? All of the computations are in NumPy and SciPy. They're very easy. The state management changes though, right? So the state management of where you keep the rewards in these distributions, like sometimes it's in memory, sometimes it's in a database, sometimes it's distributed across multiple nodes. So actually the implementation does matter a lot with the application that you're doing. And so it didn't really make sense for me to show you any code, and there aren't really any libraries that I know of, or I didn't even need to look for multi-arm bandit libraries because they are easy to implement. In my bag, I have John Miles White O'Reilly book, Multi-Armed Bandits, and it's about 80 pages. It's this thin. I forgot to bring it up to show you guys, but hopefully that highlights how easy these things are to do, and so I hope that you will make them part of your data science practice. But when you're thinking about how to implement these bandits, you really have to think about the application context more than the code context. So the three things that you have to do in order to define a multi-arm bandit problem is you have to figure out what your reward function is, and I'd say this is probably the most important thing. You have to figure out what your policies are and what those associated actions are, and then you have to have some sort of update mechanism. The update mechanism is where most of your code lives, and that again is why it's so dependent on storage and state management and communication and whatever you're doing. Like it's a front end application, back end application. Where do you want to put things? So I'm not going to talk too much about the update mechanism, but really, what we as data scientists do is we get to focus on the reward function primarily. And frankly, it is the most challenging task is coming up with the reward function. How do you define it? Now, I think that there is a block to reward functions. People want to look for some existing continuous function and like that's the reward. And in my experience, that's never the reward, right? In my experience, what you usually do is you create a tabulated award, right? So it's a weighted sum of outcome factors. And you think like, what are good outcomes and what are bad outcomes? How do we weight these relative to each other? And then how do we score them? And there's sort of two types of scores, right? So, win or loss, like this factor happened or not, 1 or 0, right? Or you can try to come up with a continuous score between 0 or 1, right? So how many of X did happen? How many seconds did this take, right? Kind of come up with those measurements and then scale it down into the space, 0 or 1, where 1 is better, right? So if you want something that's less, then you invert that function so that 1 is better. And then you can map that reward function into your multi-armed bandit application very, very easily. A couple of notes on the reward discovery process. This is another big tripping hazard. Is one, the rewards should be native to the application. So a lot of times people will come up with rewards and it's like, okay, well, how are you going to compute that, right? Like, it's like, the reward should be like, if the sun comes up tomorrow. And it's like, okay, well, it has to be part of your application and it has to be immediately observable, right? It can't be something in the future, right? So it can't be something like, the user purchases this thing, right? Or overall cost decrease, right? It has to be immediate right then. And then this might be obvious, but it does trip people up, is that maximizing the rewards should maximize the benefit to the application, right? So you're not trying to minimize costs, you're trying to maximize rewards. And a lot of times people come up with great rewards and realize that the application is going sideways, and it's because, well, those rewards aren't actually what you wanted to have out. That was not the outcome you were looking for. So the rewards have to maximize the benefit that you want. And we'll have a couple of examples of that here shortly. Just real quick on policies. So policies define the actions that your system will take. In decision making, every agent knows its state and it knows the state of each armor policy that it holds. And then if you have contextual bandits, you combine that state with the contextual vector in order to describe the action. This has to be a numeric representation, right? So I kind of gave you a strategy of how to think about that numeric representation, but it's the same thing as defining like an instance for machine learning, right? You want to use a noun to describe the thing that you're trying to describe, update the state. So like a user context, and using that noun, and then what are the numeric properties of that noun? That's sort of how you get to that contextual vector. And finally, the update, this again is very simple. It's just a probability distribution calculation. Most of these things, computations are associative and commutative, so they can be parallelized. And I'll actually show you an example of where you have a system made up of multiple agents, and you can see that multi-armed bandits can lead to emergent behavior, where you have sort of a simple system of local state leading to a global behavior overall. All right, how much time do I have to? 7 minutes. Okay, great. So I'm going to go through one. This is a real world example that we implemented at Rotational. And then I'm going to go through some more theoretical examples just as a way to show you how this creative problem solving process works when thinking about multi-armed bandits. So at Rotational, we run a global system. We have data centers in Singapore, in Germany, North America, Australia, and This is for a professional working group. It's not a profit organization, so it's really important to us to reduce costs, and we don't want to use Spanner or any expensive tools like that. So we developed a system that synchronizes data between these servers, and what we notice is that the costs increase the farther away data has to replicate, right? So it's cheaper to go from, Singapore to Japan than it is to go from Japan to New York, right? That basically makes sense. In terms of replication, each server chooses another server in the network to synchronize with, and the best outcome, the outcome that we're looking for, is that servers choose a peer that's close by, right? And so we're hoping that an update propagates in short steps rather than in big jumps. So here's my first recommendation for you guys. If you have any type of random selection in your application, any type at all, absolutely a great candidate for a multi-armed bandit. And we even knew this theoretically. So if you look at sort of what's the best possible outcome in our server as system size grows, that's actually this green line here. This is the best noiseless example that we have, but this is our measured cost in terms of latency at the top here. So we already knew that we had a lot of room for improvement going into this. So here is what we did for our reward function, right? We want to prioritize peers in our network that the server is actually exchanging updates with, right? Because that's costs that you're paying for a replication if they're not doing any replication. So prioritize that. So in our reward table, we said, okay, well, if you synchronize at least one object, and this is two directional, right? So if I'm sending you an object, I get a score of 0.25, and if you send me an object, then I get another score of 0.25, right? And then if it's more than one object, then we give you a bonus, right? Where, synchronizing more is better, right? So we give you this bonus of 0.05. In network terms, we want things to be close, right? And close is measured by ping latency. So if the ping latency is less than 5 milliseconds, we assume that you're local. And so we give you a bonus. If you're local, you get a 0.1 bonus, right? And in fact, you get 2 bonuses, right? Because we also have this regional benefit, right? So if it's less than 100 milliseconds, we say it's in the same region, you get a bonus for that. If you're local, you get double the bonus, right? And so this is our reward function. You can see this is just a simple summation, but these are relatively weighted, right? So we're saying that at least one object is more important to us than multiple objects, whereas local versus regional, is double that. And you come up with this reward function. Here was the outcome for us. This is what the network looked like in terms of data synchronization before. After, we had a much less hairy ball of graph here, and we ended up saving about $600 a month implementing these multi-armed bandits. So it was a very good outcome for us. All right, I'm running out of time, so I'm just going to quickly spin through these last 2 examples. The news aggregator, we want to rank or provide interesting news results to the user based on their preferences. So just talking about simple solutions here, right? We need to figure out how to develop policies, right? Now, I think our instinct might be to go to a per user policy, but that you end up with a lot of agents and a lot of state that needs to be maintained. And so rather than, using per user, think about using semi-personalized clusters, right? So create a bandit per groups of, similar users. And then again, thinking about the context vector, at the time of selection, what changes? The other thing I want to note about the reward function is thinking about explicit versus implicit signals. So explicit signals are when the user does something, right? Clicks on a thumbs up, thumbs down, saves for later, highlights notes, just does those actions. But there's also a lot of implicit things that you should embed into your reward, right? Time on page, associated reading, scrolling behavior. And a big question for multi-armed bandits is, how often how can we get those implicit signals? And then I'm sorry that I'm just speeding through this, but the last one I want to talk about was sprint prioritization. This is an example of the time-bound problem, right? So the idea for this one was, if we have a sprint of 2 weeks and we want to be able to have, at any time of day, the engineer has to ask the system, what should I work on? Or what's the highest priority task that I should work on? Well, you have to have the Bandit algorithm operating all the time. And so the idea that we came, and there's no time for a longitudinal study, right? That explore, like, you got to have knowledge soon. So what we came up with was a game, right? So prior to sprint planning, you have all your engineers play this game where they say this one is a higher priority than this one's a higher priority than this one. You do the same exercise at sprint planning, you do the same exercise during stand-ups, take 5 minutes, everyone plays this game, gets the multi-arm bandits trained up, that reinforcement learning, and then you can use rewards like number of points, blockers removed, that kind of stuff. You can come up with these really creative solutions to interesting problems and develop them really very quickly and get those experiments running in real time. So thank you all. Multi-arm bandits. I guess I don't have time for questions. No, everyone wants to go to lunch. You can find me after if you have any questions.
Thank you all so much. We're at 12:35, so it is lunchtime. A reminder, there is a book signing and author talk during lunch, so if you want to go talk to any of our wonderful authors, you should do so.